Very great. So yeah, it's my big pleasure to introduce Aarti Singh, who is an associate professor in the machine learning department at Carnegie Mellon University. And her research interests include virtually all areas of machine learning, in particular deep learning, to which she's been contributing for quite a while. She's been working extensively on trading off computational efficiency and statistical optimality, and also worked on active learning, reinforcement learning, and really name it. Today, she's going to talk about her work on local signal adaptivity with feature learning in neural networks beyond kernels. So without further ado, take it away, Aarti.
All right, thanks, Lars. And thank you all the organizers for the invitation. So I guess I'll get right into it. First with a disclaimer, this is a very fresh piece of work that we are still tying up all the loose ends for. So yeah, but I hope that there's a coherent story that sort of will be a little bit convincing. So it's centered around this idea of local signal adaptivity to essentially show a gap between neural networks and kernels based off of course, the feature learning capability in neural networks. So maybe I'll start by first describing what we mean by this local signal adaptivity. Okay, so the idea is that we basically, wanted to capture in a toy model, but capture what one of the key properties of natural images is, and that is that there is a small set of localized features that determine the label, right? So in these images, these are all drawn from ImageNet. You can see that there's like the bus, right? And you can think of that as, of course, like this might occupy multiple patches, right? But it's confined to a few patches. And then there is background, right? And background doesn't necessarily mean noise, though we will talk about it in the like calling it noise in this talk. But essentially, it means anything that has features which are irrelevant to the label, right? So you see a lot of like buildings and stuff in this bus image. And maybe some trees, right? Those are all irrelevant if this image is actually labeled as a bus, right? And same for some of the other images you see here, that typically the signal is confined to a small set of patches, and other patches are sort of background. And so we wanted to see that this is one of the key features, and neural networks being adaptive to adaptively learning these features, right? Can we say something about the separation from kernels in this setting, that they can find this localized set of features while discarding the background patches? And of course, some evidence for this comes from the observation that in practice, many of the neural networks actually tend to be sparse when they are trained on natural images. So this is an observation that has been reported multiple times. We wanted to see it for ourselves. So I guess we ran this. I believe this is a wide ResNet. I'll talk about the experimental setup more later. But essentially looking at how the number of active neurons decayed per layer, right, as the training progresses. So we see that a lot of the neurons, right, are set to 0, which is effectively equivalent to zeroing out certain features, right, and retaining only a small set of features that are sort of localizing the signal in these natural images. So that's sort of like the high level motivation for looking at this kind of local signal adaptivity. And the highest level message, right, that we were going after and that we prove is, I'll get into the more technical version of this toward the end of the talk, but essentially it is that a small convolutional neural network, when it is trained using standard like stochastic gradient descent from random initialization, can efficiently learn this local signal and threshold out the noise in the other background patches in polynomial time and sample complexity, right? Whereas the corresponding convolutional neural tangent kernel, so we focus specifically on the neural tangent kernel corresponding to the same architecture as the convolutional neural networks for which we have a positive result, and show that the corresponding convolutional neural tangent kernel requires a comparatively larger model. Basically meaning it requires many more filters, many more features it needs to extract to be able to accomplish the same goal. Okay, so with this sort of goal in mind, let's get into the more specifics. And I'm happy to take questions in between as well. I don't know what's the protocol, but please feel free to interrupt. But yeah, maybe before I do that, actually, I wanted to just give maybe lay of the land in terms of course, there are several papers that have focused on showing this gap between neural networks and kernels. And just to put it in context, there is a bunch of right line of work, as we just saw, on quantifying the approximation gap, right? That there are certain function classes which can be efficiently represented, right? So not necessarily learned, but efficiently represented using neural networks, whereas they cannot be represented as concisely using kernels, right? So there's a lot of excellent work in this direction, focusing on different types of classes, including smooth, Lipschitz smooth, Holder smooth, Bezow smooth, right? And many other variations. But they do not focus on efficient learnability, right? So one of our goals was not just to show approximation gap, but to actually say that these can be efficiently in polynomial time and sample complexity, right? We can learn these. Then there is a lot of work on regression, and some of it does show efficient learnability as well. Not all of these papers, but some of them do. And I guess the distinction we draw is that our motivation really was from classification setting. So we did not want to say that you fit the label exactly, but right in under this sort of 0-1 loss that classification cares about, and motivated by, again, this observation in the natural images. I did want to point out one paper that does consider classification, at least to the best of our knowledge, where they do show a gap, but it is in terms of hinge loss. And this is the paper by Daniele and Malak. And they have some very nice results, in fact, quantifying that the separation gap in particular is like exponential, which is something we won't get to, but we will focus on getting 0-1 classification error and proving guarantees on that, learnability guarantees. Now, the model that I'll present, actually it'll come on the next slide, does have some correspondence to some of these works which have talked about learning a hidden subspace. So in that aspect, you can think of this, our work also as having a hidden subspace, but it is not fixed. So the patch in which the signal can appear can be anywhere in the image, and that makes it slightly distinct, though along the similar lines as these other papers, where Daniele and Malak, for example, looked at parity functions, right? Whereas again, our model was more going after what happens in natural images and can we sort of abstract away the localized signal property. Yeah, the other paper by Gorbani also, I think, is on mixture of Gaussians. So it's related, but does not exactly get to the same sort of idea behind natural images. In terms of lower bounds, there are two flavors. There is a bound that shows, that helps establish that neural networks are better than any kernel method or essentially a linear learner. These are much powerful bounds. And as I summarized right in the brief takeaway message, we won't get to that, in particular because these are very hard to prove for classification, right? In fact, even for kernel settings, classification lower bounds are much harder and in fact don't even exist in most cases. The other flavor is neural networks and showing how they give an advantage over the corresponding neural tangent kernel. And our lower bound should also be interpreted in the same line of work, that it is showing a gap between one convolutional neural network that succeeds and its corresponding neural tangent kernel. Okay, so here's the formal setup then. So thinking about, these images which have localized signal, for example, the boat in this natural image here, right? We imagine our model to also consist of a bunch of patches, and the signal is contained in one of those patches, right? And all the other patches have background noise that's irrelevant to the classification task. The way we quantify this is via a generative model for each patch. So I is a patch, and the value of the input, right, xi for that patch is given by the label times a pattern that characterizes the signal, w star, in the signal patch, which is I star, right? And this pattern has norm 1 for simplicity. And the other patches have noise. And for simplicity, again, we consider Gaussian noise. But as I said, we believe these results can be extended to the setting where it is some other noise, but something that's does not essentially have a large projection onto W star, right? Or is basically irrelevant to the label determining function, right? In determining that. So so we consider that the noise for simplicity is again just IID Gaussian noise, and every patch is d-dimensional, right? So the setup is there are k patches, one of them is signal, and the remaining are noise, and they're all d-dimensional patches, right? So signal is confined to one of them. And in terms of like scaling, so what we consider are there are these three problem parameters that I just defined: the number of patches k, the dimension of each patch D, and then the noise variance sigma, right? The signal, in this case, the norm of W star is fixed to 1. So one other thing I wanted to mention is the key difficulty, or where the separation gap comes from between neural networks and the corresponding kernel, is coming from essentially the number of patches increasing and how the noise scales with that. So that's the main sigma and k are basically this relationship is what we'll care about. Now D plays a secondary role, and we chose not to focus on it in this talk. So we simply assume that D grows with k, but that is actually not what really causes this difference. So for simplicity, we assume D grows with k, even though we believe that actually this assumption we can relax. But so far we'll go with it. Okay, so if D grows with k, then essentially the problem parameters are k and sigma, right? The amount of noise in the background patches and then the number of patches. So our work will focus on the high noise setting, which is where we can show a gap. But before we do that, let's consider the low noise setting. So the low noise setting is essentially where the noise standard deviation omega is order 1 over root k, right? So our signal patch, right, if suppose you knew W star, right, it has a contribution of 1, and the noise that you accumulate over the other patches, right, would be k sigma square if you just used a standard, what is called in signal processing matched filtering, right, with W star, or if you want to think of it as a like linear classifier, then you can think of it as a linear classifier. That's a convolutional classifier, right? So specifically what's written there, it's just the sum over all the patches, and you're just taking the input in that patch and matching it with W star, right? So this is just a linear classifier, even though it's convolutional, right? And we can see that essentially what this is doing is accumulating just the noise in all the other patches, which scales like k sigma square because there are k patches. So as long as k sigma square is less than the order of magnitude of the signal, which is 1, right, this is linearly separable. So this linear convolutional classifier works if the noise is low in the sense that it's less than order 1 over root k. So clearly that's not where we'll see a separation, right, with respect to kernels. So what we consider is the high noise setting. In particular, we set sigma to be log k over root k. So it's growing slightly faster than root k. And actually, this is another thing where we can potentially tolerate much higher noise than log k using a CNN. But our initial focus, and as I said, like this is fresh work, was on just showing the separation. So we will use the scaling throughout the rest of the proof, though I think most of the pieces do go through when you let sigma bigger than log k over root k. And yeah, we hope to formalize that soon as well. But even with sigma equal to log k over root k, this problem is not linearly separable, right? So the above convolutional linear classifier will not work in this setting. And this calls for that we actually need to, right, instead of just aggregating the noise in all the patches, you need to identify, right, which is the signal patch, which is the noise patch, and be able to threshold out the noise before actually aggregating it, right? So that seems key to being able to tolerate higher noise levels. And this is where the localized signal, the importance of localizing the signal patch or the local signal adaptivity of neural networks comes into play. So going with the model we have, the following simple convolutional neural network we'll show works in this case. You can think of, once again, x1 through xk plus 1 are the k. I've been calling it k, but it's really k plus 1 noise patches because we consider k noise patches and 1 signal patch, but yeah, it's order k. Right, so those are the different noise image patches. And we assume that we have knowledge of the patch and the signal is confined exactly to one patch. So we can use the following convolutional neural network, which has two convolutional filters given by W and minus W for each patch. So every patch, you have a filter with weight W that's applied and B as the threshold, which is not shown in this image, and also minus W. And then so every patch maps to 2 nodes in the first hidden layer. And then these are just combined using a non-trained, right, layer where they're just combined with +1 and -1 weight, right? So the form you can see above is a ReLU applied to this linear convolution from the first filter minus the ReLU from the other filter essentially serves as a soft thresholding of the input, and then you're just summing over all the patches. Right? So the idea is, again, that these two ReLUs act together to threshold out the noise, right? They'll retain the signal. And then when we combine all the information from all the patches, the noise would have been reduced enough to be able to learn it in the high noise setting. All right, so I hope the setup and the architecture is clear. Okay, maybe a few more points. So we focus on the logistic loss for the training, right? So our error guarantees will be for the 0-1 loss, but we consider that the model is trained using the logistic loss. So the form is given there. This is standard. We also assume that we use stochastic gradient descent for training, and in particular, the mini batch version of it. So this is also fairly standard, but I just wanted to show it because there are certain things in it that need to be highlighted. One is the initialization of the weights. So the threshold, right? So B serves as a threshold, and that is initialized to be just 0. And the W, right, which is the convolutional filter weights, they are initialized to be a Gaussian with mean 0 and variance sigma naught square, right? In particular, again, we let sigma naught, maybe this is the point I wanted to highlight, decay as the number of patches grow, okay? So that's an assumption which will be made for both, of course, the NN and the NTK when we analyze it. Another part is about the learning rates, right? So we also let the learning rates decay as 1 over poly k. But in particular, we let the learning rate for B be smaller by a factor of k than the learning rate for W. And this is really for ease of analysis. Otherwise, the analysis is really messy for analyzing stochastic gradient descent. And this essentially will help us say that we can study first what happens to W, how our weights align with the true signal pattern, right? And then the threshold will kick in, and then the threshold will grow to remove noise. Okay, so that helps our analysis sort of break it down into 2 pieces where we are first finding the signal direction, right, trying to align with it, and then thresholding out the noise. And the rest is standard. So for a bunch of iterations going up to capital T, we get a mini batch of data. That's, again, a small polynomial in K. We compute the gradients, the empirical gradients, and then do the SGD updates. So I guess before we go on, a couple more points. One is that this will mostly focus on the population gradients for the analysis, but since we assume a mini batch, a fresh mini batch of size poly k at every step, so we can show concentration, right? That with high probability, the empirical gradients converge to the population gradients. So this part is taken care of, and for the rest of the proof, we'll only focus on the expected value of the gradient. And also just about the stopping time. So essentially we are saying there is no stopping time as such specified, but basically we're going to do the analysis of T is the time when your probability of error falls below 0.01, some fixed constant, right? So for all times before it, the probability of error is larger than this constant. Okay, so the way our analysis works is we'll analyze first, as I said, like what's happening in the signal direction. So we are going to look at the gradient of the loss, the logistic loss that we are training, along the signal directions. So that's the gradient and dot product with W star, which is the signal direction. And we can show that the signal patches contribution is large and negative. Okay, so this is going to help align W star with W. Whereas if you look at the noise patches contribution, that scales as W dot W star, right? How well it aligns, times sigma square k log k, right? And if you remember, right, in the high noise setting, right, sigma square is larger than 1 over k. So sigma was larger than 1 over root k, right? It was like log k over root k. So here we'll get this thing to be growing only logarithmically. The product k log k times sigma square is only going to grow logarithmically in k. So essentially what this implies is that for, right, before your probability of error drops below 0.1, for any time point before that, right, as long as we haven't, right, already achieved a large alignment with the signal patch direction, then with high probability, the loss of the, the gradient of the loss along the signal direction is large, right? And it'll keep causing W star to grow, right? Or us to, the convolutional filter weights to be aligned with the signal direction until it grows past this value, which is 1 over log cube k, given our high noise setting where sigma square scales like log square k over k. Okay. So now we have established that, right, we'll keep aligning with the signal patch direction as the SGD iterations progress. We also need to say something about what happens in the non-signal direction. So W perp here will represent the W that's not aligned with W star, right? So W star was our signal direction, and W perp is the part that's not aligned with it. And if you look at the component of the gradient along that direction, then of course the signal has no contribution there, right? It's completely confined to the W star direction. The noise patch contributes. We can show that it's actually a positive gradient that it contributes, right, with high probability, and its magnitude though is bounded. So it's a slow growth that depends on the norm of that direction times again the scale log k sigma square. So very much mimicking the analysis for the signal direction, right? But what this implies now is that there is no large contribution coming from the signal patch. So the norm of the weight in the orthogonal direction actually decays, right? So there's a positive gradient, so it causes the norm of W perp to decay. So we can say that for any time before we stop, the gradient of the loss in the non-signal direction is going to shrink, right? Or actually, it is going to cause norm of the W perp to shrink. And that's really all we need, right? So we'll start at some initial value, and it is only going to shrink further. That's going to be sufficient. And then we get to the threshold, right? So remember I had mentioned that we let the step size along B, which is essentially learning the threshold, to be smaller than the step size in the W direction, right? And that's what helps us do the signal direction analysis and the non-signal direction analysis first, and then focus on B, right? So here you will see that once you have achieved a good enough orientation of your filter weights with the signal patch, then the noise threshold starts kicking in. So if you look at this gradient, right, we see that the signal patch's contribution is just bigger than -1, right, in particular. And the noise patch, though, contributes significantly in this case, and it will cause the threshold to grow. So the noise looks like W dot W star and times K to the 1/8. This comes from essentially a variance analysis of what's happening to the gradient, right? And so essentially what this implies is that for any time step, right, before our probability of error drops below 0.01, right, as long as the signal direction has aligned, right, so the convolution filters have aligned with the signal direction at a rate of like 1 over K to the 1/8, right, more than that, then the gradient of, the gradient of the loss with respect to B is gonna be ω1. It's going to be positive, right, which is going to cause B to decrease. And the threshold is, remember, is -B because it's W transpose X plus B bigger than 0, right? So the threshold is -B. So it causes B to decrease because the gradient is positive and order 1, and hence it causes the threshold to increase, right? One small point I wanted to make is, well, you might wonder what happens to the threshold while we are, right, we haven't reached this threshold in terms of aligning to the signal patch. And it is true that actually the analysis was a little more complex. So initially B can grow, but again, because we have this scaling, right, between the step sizes along the threshold direction and then the W weights, right, they have different scaling of the step sizes. That's what helps control how large B can grow initially, right? So starting at that control large value, it's then gonna keep on decreasing. But that does play a role in the analysis.
We have about 4 minutes left.
Yep, that should be fine. So yeah, so just to summarize, then we can put all these pieces together. We essentially show that the signal alignment continues to grow, and it grows to something like 1 over log some, right, poly k. And this grows at a rate of, right, whatever is the step size. So because our step size is decreasing 1 over poly k, this only takes poly k iterations, right? And then the threshold has to increase at a rate of the corresponding step size to match the largest noise along W, right? The threshold should increase whatever beyond what's the largest noise, which is the norm of W times sigma root log K. That's just the maximum of K Gaussians. And we can bound the norm of W by bounding how much is the alignment along the signal, which cannot grow beyond order 1 as long as the probability of error is still large, right? And then the norm of W perf, which keeps on decaying starting from the initial value, which again, because of our scaling of sigma naught, is actually shrinking. So we have that our norm of W is order 1, and hence we only require, again, poly k iterations because eta b, the step size along b also scales as 1 over poly k. All right, so yeah, this leads to poly k computation and poly k sample efficiency. Now, I'll go over the lower bound quickly. So basically, this is looking at the corresponding convolutional neural tangent kernel. So we have a fixed set in this case of J0 weights, right? And for any threshold, we can give it the best possible threshold it may need. We look at this thresholding, right? Similar to the ReLU, because this is essentially coming from the gradient. And then learning the WJ weights that align with, which are also convolutional and align with the different patches. And we allow up to M filters, right? So we only had 2 filters in the CNN upper bound. Here we allow up to M filters. And as long as we are still in this high noise setting, right, which is the same scaling we looked at before, we see that if the number of filters is a constant, right, it does not scale with KRD, then we can have that with high probability over the random initialization of these fixed weights that you're matching with, right? For every set of weights that the CNTK can learn, and every set of biases, the probability of error is bounded from below. I won't go into the details of this, but that establishes a separation because, yeah, you need the number of filters or the number of features learned to be bigger than D or scale with D or K. I'll just show one set of results maybe because I know I'm out of time, which is we tried this like a big wide ResNet, and we tried to simulate it by putting a CFAR10 image, scaling it down to 16 by 16 and putting it on a 30 by 32 noise background. And then we vary the intensity of the noise background and see how the performance looks like. So you see that, yeah, just the fully connected convolutional right wide ResNet, right? It stays stable as the noise pixel intensity is increased, whereas the neural tangent kernel goes down in agreement with what the theory predicts. We did it for some other settings. These are simpler settings, only CFAR2, where the initial gap at 0 noise is smaller, but we still see this degradation of the NTK with increasing noise, whereas the fully connected net stays much more stable. And this one was where we put, so we were trying to find vehicles. So the vehicle is in one of the patches, but the remaining are animal patches. So it's not just varying, it's more complicated background, I guess. And a similar thing is observed. So yeah, just to maybe mention some open directions, I've already mentioned like, yeah, we can investigate going beyond, like what's the largest noise you can tolerate and still have this gap hold. There are other noise models that I think can be addressed beyond the Gaussian. One key piece was non-alignment of the signal patch with the convolutional filters. This is technically much more challenging, but will really make it closer to reality. So that's, yeah, that's an interesting direction to pursue. Improve lower bounds for all kernels. We only show lower bound with respect to NTK. So clearly it will be good to have a broader lower bound, but I think the challenge is again dealing with classification lower bounds, which are very, very hard to prove. And of course, extension to deeper networks, which will come when we allow for non-signal, non-alignment between the signal patches. All right, so I'll end there. Our paper will be on arXiv soon, and I should really thank Stephanie, who's done a great bunch of work. Stephanie and Ezra both, in particular, Stephanie dealing with like a lot of truncated Gaussian arguments. She's spent a whole lot and is an expert on that now. And Yuanzi, who is our collaborator on the project. So thank you.
Well, thank you, Aarti, for this excellent talk. We have time for a quick question or two, and then I think in Cambridge there's tea time also, which can probably be used for the virtual people to chat more with Aarti. So does anyone have a question? It's burning. Drop them in the chat or just ask them. I mean, Renee has a question. Okay, go ahead.
Hey, Aarti. I wanted to understand a little bit the significance of the problem itself, and particularly connected maybe to the line of future extension. So the closest problem I could think of in computer vision is really object detection, where you want to detect multiple objects, they have different scales, and you don't know how many. And so relative to that, here, I think there is the assumption that there is only one object and that the grid where those objects lie and the sizes is predefined. And also that the background model is just Gaussian relative to what's more typical, that you've got sort of a cluttered scene behind. So in terms of the extensions, it seems to me that it's not just the deeper network. I think having matched filters is probably still good. And in various ways, even deep ReLU networks can be considered as match filters. But really, I think the assumption that the size of the filters is the same as the size of the object, the fact that there is only one object, the fact that the locations of the objects are aligned to the grid. So those are all assumptions, I think, from an object detection perspective. So could you comment a little bit more of where do you see this problem being actually applicable?
Yeah, so I mean, first of all, this was just a demonstration of, right, like one possible explanation for the gap, which is coming from the noise thresholding, right, and localizing the signal. And you're right, this is a toy, abstraction of it. I did want to mention a few points. One is, if the signal actually was contained in more than one patch, actually, I think the analysis does extend to that much more easily, right? It could be, as long as it's still like aligned with the patch. So the main thing is like going beyond that alignment, right? Which is what you refer to. Also, I think extension to noise background that is not Gaussian, but has like, again, a low alignment with your signal patch should also be not too hard. In fact, I think there are other papers that have tried to do that in different setup, but they don't show the kind of noise separation we do. So I think those two pieces, the signal being present in multiple places, the signal actually patch occupying the full D-dimensional space, as opposed to having a signal, right now it's not spanning the full D space. That's also an extension I think we can easily work in. In fact, we are working on that, where you say the signal is like sum of some D, whatever patterns, essentially. So all of that is easy. I think going where we have non-alignment, I think that's where the analysis is possible, but it does get much more tricky, because then you are only capturing a fraction of it, and depending on what fraction you capture, and then you have to talk about like how you adjust the stride. But really, if you think about it in practice, that's done by hand tuning, right? So there is, right, people are playing with the stride of the filter and size of the filter. These are not data learned quantities as such. So yeah, so I guess you're right. I think those are all great points for extension. But our idea was just to show a different way of looking at the separation that hasn't been seen so far.
Thank you.
There's another question in the chat window by Semi. So thanks for the talk. Are the bound properties specific to some activation functions? More general, do you think they are specific to CNNs?
So yes, our separation is, if I understand the question correctly, our separation is specific to CNN in the following sense, that it does kick in when your number of patches grows, right? So it is about localizing the signal, right? So if you only consider, for example, a single patch, right, and that just has some signal pattern versus not, then you don't see this kind of gap. So that part is crucial. But I think that's also where it was actually motivated by natural images and the convolutional neural networks being the right fit for that, right? So yeah, that is needed. And in fact, that is the gap we are trying to focus on here. Whether it is specific to the activation function, I think like essentially all we need from the activation function is a thresholding effect, right? So as long as we get the soft thresholding effect, which you can get from other activation functions also, the analysis is potentially extensible to that.
Okay, very well. I think that should answer that question.
Thank you. Yes.
Hopefully. Great. So yeah, then let's thank Aarti again for this great talk. And the Cambridge people can move on to a tea time. And I think the virtual participants are on their own. We can stay here and chat more. And we continue in about 25 minutes. So don't go too far.
Yeah.
Thank you.
Thank you, Aarti.
没跟他聊天的，我跟他聊过一次，但那次咱没有出名。
How was the conference in general? How was it?
Aarti, can I also ask you a very question?
Sure.
So when you looked at the sparsity, at the very beginning, the sparsity of the time wave, and you said that, oh, that means that some of the features may not be needed.
Yeah, can you repeat? I didn't get the starting.
Oh, I guess they're too long. So when you talked about the sparsity of the trained weights, is it important to look at maybe grouped sparsity? So that means that maybe like a complete filter would be 0, because if there is just one element in there, then I would still need that input feature channel, right?
Yes. So, but yeah, I think looking at the sparsity over the different layers, though, right, does
Okay.
point to that a whole group is.
So that's what you look at. Okay, yeah, that makes sense. Okay, very well. I'll take a quick break. I'll be back in a few minutes. And yeah, thanks again for coming around and giving the talk.
Thank you. Yeah, thanks for the invite.